Okay, welcome to Math 65. Today we're going to learn about solving quadratic equations by factoring. So we just spent a whole entire chapter learning to factor, didn't we? How many people feel like they know how to factor now? Good. Kind of, right? And how many people like factoring? You can admit it, you can admit it. Oh, look at that. Yes. Well, you're in for a lot of fun because we get to do a lot more factoring. Okay, so we were just talking about the difference between, in Math 60, we learned all about linear equations. And a linear equation would be something like this: 6x plus 3 equals 21. Okay? The goal in solving this linear, and this is, by the way, a linear equation. We call it a first degree equation because we have the exponent is 1. Okay, you don't see that exponent, it's implied. So it's a linear equation, and our goal is usually to get x by itself. Well, the problem when we solve quadratic equations is that we have x's in multiple places. So this is an example of what a quadratic equation looks like. It has ax squared plus b times x plus c equals 0, where a, b, and c are real numbers. Why can't a equal 0? Well, if a equals 0, you wouldn't have an x squared, so it wouldn't be quadratic anymore. So the fact that it has this x squared term makes it a quadratic. That's just the name of it, just like we call this linear, okay? So we refer to this form as standard form of an equation. And notice it's usually a trinomial. Now it can be that b and c could be 0. Ax squared could still be a quadratic on its own, okay? Because 0 is a real number. So what we've been practicing is we've been taking quadratic expressions. What's the difference between an expression and an equation? Oh, that's coming up, that question. Yeah, expressions have no equal sign. Okay, so, and an equation has an equal sign. So some things that you cannot do with expressions, you actually cannot solve them. What have we been doing with expressions? And I'll give you an example. X squared plus 2x plus 1. This has no equal sign, so that makes it an expression. What was something that we've been doing with these expressions? We've been simplifying. Good. You can simplify. What else have we were just doing with them in the last section? Factoring them. Yes, we can factor them. We can also add, subtract, multiply, and divide expressions. Okay, but we can't solve expressions. Okay, with equations, they do have an equal sign. So it could be something like this: x squared plus 2x plus 1 equals 0. Could we still factor that? Would it be possible? If I can factor this, could I factor this? Yeah, we could factor. We could factor, and in fact, we're going to be factoring because we're going to be solving. So let me explain how this solving works. The problem that we have with solving something like this versus solving a linear equation is, since we have an x to the first power and an x squared, they're not alike. We cannot combine them, so we have a really hard time getting x by itself. So in this standard form, the problem with solving it is I cannot isolate x. Does everybody agree that that's true? So what factoring does is allows us to get two numbers that we would multiply together, and we always have to set it equal to 0. So this is called the zero product principle. The product of two numbers or more is equal to 0. If it is equal to 0, then at least one of the numbers must be 0. So, for example, if you have A times B, the only time you know what A or B is if it's equal to 0, because if it's equal to 0, it must be true of one of those numbers. Each one has to be, one of them would have to be 0, right? Because if I said that B was equal to 0 and A was equal to 5, still 5 times 0 equals 0, correct? So it doesn't matter what the other number is, so long as one of them is 0, the product would be 0. That's called the zero product principle. That kind of makes sense, right? So we usually take very simple math and then we use it in more complex situations. So notice this form right here. We call this form, so back up here, this was standard form, right? What kind of form is that quadratic in? And how do you know it's a quadratic, and how do you know what form it's in? If you were to FOIL it out, it would have an x squared. That's why it's quadratic. What do we call this form? It's not standard form. It's factored form. If you expand it, you would probably multiply, right? Expanded would mean to multiply it out. So here, this is in factored form. It's a quadratic because if we did expand it or FOIL it, we would see that we get an x squared. Now, what we're going to do is apply the zero product principle. Since we are saying this binomial, which counts for A, times this binomial, which is like our B in this case, equals 0, then I know I have a solution to this if I set x minus 5 equal to 0 or x plus 1 equal to 0. Isn't that true? If one of these is 0, the whole thing will be 0. Well, what number would I subtract? What number could I take away 5? Well, essentially, this becomes a linear equation. What number minus 5 gives you 0? Yeah. And if you didn't know that, you could just solve x equals 5. There I have isolated x, right? Here, what would x have to be in order to give me this equal to 0? -1, exactly. X equals -1 would be the second solution. So actually, these are solutions. And what can I do to see if they're correct if I really wanted to know if I have the right answer? Yeah, check. So my solutions are -1 and 5. Remember the set notation from Math 60? We use that when we have a solution, we put it in set notation. Do not put parentheses around -1 and 5, because if you do that, check by plugging in. Just want to, but you can kind of see that will work right now because it's pretty obvious, right? But do not write it -1, 5. Don't write it that way, because that ordered pair, yes, means x and y. Okay, that is an excellent question because we have two solutions here. In the past, in our linear equations, well, remember when we did linear equations, you could have one solution, you could have no solution, or you could have infinite solutions. In this case, because we have x squared, we have two solutions. And I think I can come up with an easy example of why that is. I'm just going to slide the paper up so I have a little bit of room to write up here, okay? Imagine for a minute I have x squared equals 25. Can you tell me any number that I could multiply by itself and get 25? 5. So x could be 5. Can anyone think of another number? -5. Oh, such is the quadratic. So for a quadratic, not always, but sometimes we will have two solutions. And I think that's an easier example. Does that kind of drive home why? It's going to come up a little bit more when we get to graphing quadratics too.
But with this one, it's x equals 5 and x equals -1.
Yes.
How do you square two different numbers?
Well, let's get back to that when we get to a different equation, okay? I'm going to come back to your question. Okay, so for now, let's just look at these ones because these are in factored form. If I did want to check, I didn't complete my check because I kind of ran out of room. But if I were to check, I would plug in 5 in both places, right? And then I would see if it worked out. Well, I can see right away if I plug in 5 here, I'm going to get 0. So does it matter what number I multiply it by? I mean, it's going to be 6, but that doesn't matter because it's still going to equal 0. So that works out. Like I'm just doing a mental check, right? So what would I do to solve for x here in this factored form? I'm going to set each factor to 0 to figure out what number could go here or here and give me a 0. So here's one factor is 3x plus 4. I set it equal to 0. And then my second answer is going to be 2x minus 1 equals 0. Okay, so how am I going to solve now? What should I do to try and get x by itself in both of these examples? So I'm going to subtract 4, right? I get 3x equals negative 4, and then divide by 3. So I can get fractions. X equals negative 4/3, yeah? Here, what do I do to get x by itself? Add 1, 2x equals 1. What should I do next? Divide by 2, and I get x equals 1/2. So my solution set would be negative 4/3 and 1/2. And again, oops, my curly braces didn't come out so beautiful that time, but that's okay. So if I want to check, and I always suggest you do, check, I can plug it back in. So I can take the negative 4/3. Here's 3 times negative 4/3 plus 4. And if this gives me 0, it really doesn't matter what negative 4/3 would be in the other example, you know, but you can still plug it in there too. So what happens with when you plug in negative 4/3 here? What can we do to simplify this? Yeah, the 3's, don't they cancel? Dealing with fractions. Negative 4, this becomes negative 4 plus 4, which is 0. So, I mean, technically I should plug it into both places, but I just didn't want to deal with a fraction in that in that situation. Let's plug in the 1/2 in here just to make sure we get a 0. 2 times 1/2 minus 1. Let's see if we get 0. So what would we get there? What's 1/2 times 2? 1. What's 1 minus 1? Okay, so technically you guys know I should be plugging it into both places, right? I'm just avoiding it because I don't want to do that math. Times 0 is going to be 0. Do you agree? Any questions so far? So in these two examples, we actually didn't factor, did we? It was already factored for us. Most of the time, what we're going to see is that the examples are mostly not going to be factored, okay? Those were just to get us started. So the process to solving a quadratic equation is going to be to always simplify it as much as possible, simplify the equation using the distribution and combining like terms to put it in standard form. Now, standard form is always going to be this, and it always has to be equal to 0. Any thoughts about why does it have to be equal to 0? Because the only way we could use the 0 property is if it's set equal to 0. For example, if I told you that a times b is equal to 3, do you absolutely, without a shadow of a doubt, know what one of those letters is equal to? Not necessarily. Not necessarily, it doesn't have to be. So my point about this is this only works, the 0 property only works when you have a times b equal to 0. Okay, because there's no other number where you're going to know without a shadow of a doubt what one of the numbers is. Do you get that? Okay, so the next step is to isolate, move all of the terms onto one side so that it has 0. Well, that was what I just said because right here it says equals 0. Okay, and factor the expression. So this is where we get to use our factoring skills. Going to be super important in this class and in your later math classes. Apply the zero product principle by setting each factor equal to 0. Solve the equations that result after the zero product property was applied. Check to see if that works. Okay, so here, the first thing we're going to do is let's ask ourselves, is this right now set up in standard form? It is in standard form, okay? Because remember, standard form is just this. And it's already equal to 0, okay? So we actually don't even have to do step 1 and step 2. Step 3 is we're going to factor it. So this is where we get out our factoring skills. Who thinks they know the factors? Oh, how'd you come up with that so fast? Oh, x minus 3, x minus 5. Do we all agree that those are the correct factors? Are we remembering how to factor? Now, what should I do next? After it's in factored form, what's going to be my next step, step 4? And? Okay, so we're going to solve those. And what do we have? We're going to add 3, x equals 3, x equals 5. And so those are our solutions. Solve, let's state our solution. The solutions are 3 and 5, and I'll put those in set notation. Remember, it's not an ordered pair. There's no parentheses there. And then let's look at how the check works. I think this might maybe answer your question that you were asking earlier. Why can we have 2 solutions? And it's because they both end up working. It's actually going to be because this, when we get to later on in this chapter, or maybe chapter 9, I think, we're going to be graphing parabolas. And what you're going to find out, I might as well just tell you this now. Why keep the suspense lingering so long, okay? So imagine this is the x-axis and this is the y-axis. You are setting this equal to 0, which actually means that y equals 0. Does anybody know, where does y equals 0 happen on the graph? On the x-axis is y equals 0. So if you say that your solutions are, these solutions are x values, okay? You don't have to know this just yet. This is a little sneak preview of what's coming up. What that means is this parabola comes and it touches down at 3 and 5, comma 0, right? So when we are solving a quadratic, later on when we learn about the graph of a quadratic, I think this is really the best way to answer why you have 2 solutions. It's because the quadratic equation, when we graph it, it does have this symmetry, okay? So we'll get to all that later. That's coming up, but that's trying to answer the question, why do we have 2 solutions? Well, we have 2 solutions also because they both work. So if I plug them in, the check looks like this. I'm going to take 3. Don't forget to use parentheses when you plug in numbers, even though this is a positive 3, minus 8 times 3 plus 15. And if you plug that in on your calculator or do the math right now, 9 minus 24 plus 15, it will equal 0, okay? Trust me that it will equal 0. No, don't trust me. 9 plus 15 is 24, minus 24 is 0, right? The second check, remember I have 2 solutions, so I need to check them both. So for the check, I'm just taking the x value that I got and I'm plugging it in. 5 squared minus 8 times 5 plus 15. Is it equal to 0? This is 25 minus 40 plus 15 equals 0. Well, if I owe someone $40, but I have 25 and then I make another 15, that's 40, right? 40 minus 40 is 0 equals 0. So they both check out. And then later on, like I said, we're going to be graphing these and we'll see how these solutions are the x-intercepts. It's always good. Repetition is good. So it's good that we've talked about that a little bit. Just only scratch the surface. Any questions so far? Now, the next few, normally I would want you to try a bunch of them, but I kind of want to show you a few strategies. So, actually, let's take a break, then I'll come back and show you a few strategies.